Hello everyone. Today I'll be giving a walkthrough on my project that is drought severity prediction for Pueblo, Colorado. Now let's start with what is a drought. A drought is defined as a prolonged period of abnormally low rainfall and it can be categorized into different categories. It can be due to meteorological effect, which is due to low rainfall. It can be agricultural, where the soil is not able to retain good moisture, affecting the soil. It can be hydrological due to the low retention of water in different water bodies, and it can be socio-economic, which is when the demand of water exceeds the supply. And moving towards why this is a problem and what is a solution for this. So, a drought is a problem that needs to be solved because there are different implications. It can be socio-economic implications for drought, and what we want is to predict the probability, length, and the intensity of droughts. And why we want to do it? We want to do it because we want to build early warning system, agricultural planning, water resource management, these kinds of processes to ease out the face of a disaster. And okay, so coming towards the county map of Colorado for 2018, we have a heat map where we see different categories of droughts ranging from D0 to D1, and white one represents there is no drought. And we see that Pueblo is a county where it's D4 category of drought, which is exceptional drought. And if we look on 2023 also, we see that again, this is a county map. This white border is a county map of Colorado. And we see that Pueblo is a region where we have severe droughts. So this was a reason why I chose Pueblo as an area of interest for this project. And moving towards what are the data points that we need to analyze a drought condition? So we need air temperature, we need precipitation, we need groundwater level, we need steam flow data, we need soil temperature and soil moisture data, and we need the drought data itself. And the different data sources that are used to fetch these data for Pueblo, we got air temperature data from NOAA website, which is National Oceanic and Atmospheric Administration, and precipitation data was also fetched from the same website. For groundwater level and steam flow, we fetched data from United States Geological Survey, USGS API. It's a Python-based API. And for soil temperature and moisture, we used United States Climate Reference Network website, and it was filtered for latitude and longitude for Pueblo County. And for drought data, we got it from drought.gov website, and this was filtered for Colorado. Okay, so let's look at the actual locations where we got different datas. So starting with groundwater level, these are the three accurate wells that are inside Colorado, which give reading of groundwater level at different instances. And this is the one that's located in Pueblo that was used in this project to fetch groundwater level. And for steam flow data, that is nothing but daily discharge data. We are using the Fountain Creek website available in Pueblo. And for air temperature and precipitation, we use the Pueblo Memorial Airport site that's there in Pueblo County. And for soil moisture and temperature, we filtered the USCRN website for latitude and longitude, specifically for Pueblo County. Okay, let's look at how the data looks like. So this is the raw data that we have from different sources that's combined based on the date. We have precipitation, we have minimum and maximum temperature, we have groundwater level, we have soil moisture and soil temperature, the SM and ST at different depths, at 20 centimeter, at 50 centimeter, and at 100 centimeters. And we also have daily discharge data, which is nothing but the steam flow data. And this is how the actual drought data looks like. It's categorized in different categories that we saw in earlier heat maps, D0 to D4, D4 being the exceptional drought category, and none being where there is no drought. And Pueblo usually lies in this category, which is exceptional drought category. And this is what we are interested in predicting. Okay, moving towards our analysis process, we started with data collection and gathering to generate a final actionable data set. We moved towards principal component analysis. And one important finding in principal component analysis is we see that we were able to reduce the dimension of data for soil moisture and temperature from 3 dimension to one. And this really helped in further modeling processes. Next, we perform clustering analysis to understand different clusters in our data, in our drought data. And if we look at different clusters with help of WCSS, that is within cluster sum of square or either silhouette method, we found that 6 is the optimal number of clusters, and that is same as the number of categories of drought we have from D0 to D4 plus none that we see in the heat map of Colorado County. So we can say that all the variables we have are accurately able to collect or represent all the categories of drought in our data. And moving towards the step four, we introduced different supervised learning models like naive-Bayes, random forest, support vector machines for predicting the drought severity or the D4 severity for Pueblo. And the final step was introducing the advanced machine learning models like neural nets for the prediction. And now moving towards the result. Okay, so let's start with the second best model that was neural nets. So for neural nets, we train different models for optimizations based on different activation functions, different number of neurons, different factor size and batch size. And this is the optimal model that was found based on the training and validation loss. We see that the training loss and validation loss both reduces over the number of epochs and they get constant or like almost constant after some time, which is a good sign. And the accuracy for this model was approximately 70%. In the recall, that is the true positive rate. The number of instances where there was a severe drought and it was categorized as a severe drought was about 66%, about, sorry, 65%, which is not that good, but yeah. And moving towards our best model, it is the random forest model, which is a decision tree based model, which is an ensemble model. And looking at the accuracy for this model, it's about 96%, and the true positive rate, which is the number of drought that were there and that were predicted by the model, is about 94%. So this is one of the best model that was accurately able to categorize the drought severity for Pueblo. And if we look at different feature that were introduced in the model and the importance of those features, we see that groundwater level is the most important feature, followed by the daily discharge rate, then the soil moisture and soil temperatures principal component analysis, then the temperature and precipitation. So this basically tells us a good story that for a drought situation to occur, there should be low groundwater level, there should be like a high discharge, there should be low soil temperature, there should be low soil moisture, high soil temperature, and these kinds of things. So this this feature importance graph basically allows us to create a story out of all the features and see how they help us to model the drought severity. And coming towards the conclusion and next step. So we can conclude that based on the model that the groundwater level, daily discharge, soil moisture, and temperature are the major indicator for drought severity. And the next step for this project would be to create engineered feature which would help us to predict this event in advance. And the short-term goal would be to predict this event at least 30 days in advance. So this is a good time frame to build some actionable strategies to overcome such situations. Right now, the project is using the actual real-time data, but we would want it to be able to predict such events at least 30 days or some actionable time frame in advance, which will help us to build or execute some strategies to overcome these events. And yeah, that was all of my presentation. Thank you.